have here is actually 1 over h naught squared. Then we have r naught over r squared. It equals to h pi g 3 divided by 3 of h naught squared times rho minus k h naught divided by h naught squared. The density, and so the critical density is 1 over the 10 that we have here. So we can write like omega, omega naught equals to rho divided by rho crit, evaluated today, and that's the inverse of this critical thing here. And what else? So we can then what we get is actually k divided by h squared r naught squared minus 1 equal, sorry, to omega naught minus of lambda. Okay? So what we have here is omega letter naught times rho m divided by rho naught lambda naught. Now I should write here as rho lambda at any given time divided by rho lambda naught. But we said that actually rho lambda is, I don't remember the exact, just a factor times lambda itself, and lambda itself is a constant. So I don't have here anything more. Plus, actually, I'm sorry, it's a minus. Let me write it here, the minus. So it's a minus. Now, omega m, so that's the term that I have here, that's the minus k. So the minus k, actually I'm taking it from here, okay? And so it's omega meter naught plus omega lambda naught minus 1 times 1 over a squared, okay? Now I know how the term, I know how actually this term behaves, okay? So eventually, what I have here is I know that actually this term here goes like a to the minus 3, okay? It's actually what it's, what's written here is 1 plus z cubed, and 1 plus z cubed is just a to the minus 3. So at the end, what I can finish here is I have an equation that I can write like this. Okay, I have 1 over h naught dA dt. Okay, so I have an a squared here, and I have to multiply it by whatever I have on the right hand side. So it's omega n. No. I have here a to the minus 3 times a squared, so it's a to the minus 1, plus omega lambda a squared minus omega n naught plus omega lambda naught minus 1, and that's it. Okay? And so now actually I can write an equation, a differential equation, where you see that I can do here a separation of variables. Here I have only dependence on A, the scale factor, the normalized scale factor, and I have here a D. Okay? So what I can write here is dA. I'm sorry, it's a square, I mean, it's a square root. Okay? That I have here. And so what I have here, I can write it as dA divided by some function f of a, and I'm going to use this function. So I'm writing it as an f of a, okay? And so equals to h naught dt, okay? So now I have here a differential equation. It's a very, very simple one. Sa is actually whatever is written here. So let me call, just to say, so this whole thing equal to this f of a. Right? And now what I can do, I can just integrate. So I can integrate it from 0 to a. And I can integrate it from 0 to t. So this is very easy, it's just h naught times t. And so doing the integral, I can find actually the relation. What I'm finding from here, I can find a relation that actually t, I'm sorry, t or h times t, h naught times t, actually equal to this integral. Okay, so I can solve actually for a, I'm sorry, for t as the function of a, you invert the relation, I mean, it's a numerical thing, right? You take any arbitrary cosmology. I didn't assume here that I have a flat model, okay, or anything. If you want to add radiation, it's just a piece of cake to add another term, and it's done. So there will be another term here with another power of, I guess it here it would be like a to the minus 2, and end of story, okay? So actually what I'm going to ask you is just, it would be nice if you have as part of your toolbox, okay, that you write yourself a small integration routine. Okay, it's nothing, it's really a piece of cake, okay? To go and to find actually t, so here you have some kind of a function of a, okay, so t actually equal to this integral, and from this you can actually invert and you find a of t, or you can call it like t of a. All right? So that's like, I think that's what people asked me, like, two of you actually asked me yesterday of how to do this kind of a bookkeeping with omega and the Friedman equation and so on. Can I go on? Is it clear what I did here? Okay. So I guess we need to ask you to have like your own table of how to calculate the relation between A and T. Actually, it's really very easy if you start from here. All right. Top hat. Remember top hat. So what we are going to spend the whole of today, I hope that we'll be able to finish it, is to talk about the top hat model. To remind you, so the top hat model, let's do it again. We are looking at, we assume that we're living in a homogeneous and isotropic Friedman universe. Okay? We take just one cut through the density. We just arbitrarily assume a center. We call it the center of our coordinate system. Any point is as good as any other point because the universe is homogeneous and isotropic. Okay, and I'm looking at the density, and I'm saying, suppose that this is the unperturbed density in the universe. So now I'm doing only one small thing, you know? And the one small thing that I'm doing, I'm just, I'm an alien coming from elsewhere, I'm from the other universe that comes to visit. I have some extra metal in my pocket, so I take the extra metal in my pocket and I put it here. Namely, at this point, I don't bother to compensate from this excess of material that I have here to come at the expense of some other region where I take this material. So I have the freedom to do it, so that's what I'm doing. And now so this is like the excess of material, and when we look at it, the profile of it, it looks like a top hat, so that's why we call it the top hat model. Now we can complicate it a bit and say, actually we have two components in the universe. That's one component. We look at some early time. In some early time, the universe is dominated by the dark matter, by the cold matter, which is combination of dark matter and baryons. But we have another component, and that's the rho of the lambda term. Okay, I cannot perturb this one because this is constant. So when I make the perturbation, I'm just perturbing this quantity, and I forget, and I keep the other component to be as it is. I cannot change it. Okay, so the general picture of how to do the top-hat model is to do it in a way that you perturb one quantity and you keep the other one as it is. You don't touch it. All right, and so, but I mean, right now I'm going to start with the top-hat model, and actually, I forget about the fact that actually I have another component, and let's say that we forget about the lambda, all right? And we do it at early time, rho lambda actually, rho cold matter is much, much larger than rho lambda, and we can really forget it. At early time, not at third. Okay? Now, because of the spherical symmetry, right, the universe is homogeneous. I put here a spherical perturbation, okay? And so I'm saying that this spherical perturbation has some initial radius at some initial time. So that's the picture of the universe of my perturbation at some very early initial time. Okay, I have this, and I'm saying I have a very special perturbation. There are different ways to set up the primordial or the initial perturbation. Like one way, I can perturb both the density and the velocity. Or I can say I'm lazy. It's good enough that I brought with me enough material to put it there, like to dump it here, and to form this excess of material. But now, once I put it there, I let it initially expand with the rest of the universe. Okay? Now imagine for simplicity, later on we'll do it with full glory for general cosmology. Let's say that we are dealing with an Alcide universe. So if I'm looking in another region, okay, so let's say that I have another region and I'm doing the same kind of trick, but this time I'm looking at the same kind of initial sphere, right? So that's like our eyes on both sides. But this time, I do not perturb the universe. Okay. Now that the Einstein theta case actually puts it in this marginal case between a closed and open universe, so that the total energy of this universe is actually zero, and as such, actually, it will expand forever. Okay. If I'm following what's happening in this, when I'm looking at the values of the sphere, imagine it's cut through a sphere. Actually, I know that R goes like T to the two cells. Okay. Now, what happens when I'm adding material here and I don't change the velocity? What do I do to the energy? This sphere that I have with the initial sphere. What's the energy of the sphere? It's now zero, negative, or positive. I'm adding more material. What do I do to the gravity? Sorry? I'm increasing what? The gravity. So namely, if I have like two, if I have like, you know, two observers that I'm putting at the end of my perturbation, one in the unperturbed case and one in the, which one is feeling a stronger gravitational field? The one that they need to perturb next to this appropriate sphere that I put there, right? And so actually, this perturbation now become bound because I have excess of material. So the gravitational field is stronger, the gravitational energy is stronger. At the same time, I didn't change the kinetic energy. I'm talking about energy per unit mass, okay? So it's the energy per unit mass, the kinetic energy stays the same. So the difference between this field and the unperturbed field is that this one is bound, the other one is unbound. All right? So if I'm just plotting here, like the time evolution of these two fields, okay, so let me call this one with this with bar on it, denoting the unperturbed, just the big universe. So for one, so if I'm plotting R of t, then actually it goes like t to the 2/3. We found it yesterday, right? Now, what about bound perturbation? The bound perturbation actually corresponding to the closed, to the omega not larger than bigger than one solution, the cycloid that we found. So actually, what this one is doing, actually doing something like that. It starts initially very, very close to the original, to the unperturbed solution. At some point it deviates, it reaches maximum expansion, and then it reaches some kind of a collapse state, kind of a crunch phase that we have here today. Right? So now, the topic model is a fantastic model. I mean, for us as physicists, we like spherical things because we know how to calculate spherical things, often, not always. But in this case, So, given any kind of cosmology, I can tell you that when I'm looking at the evolution of this sphere, this perturbed sphere, in simple words, I can say I don't give a damn for what the universe is doing. Gauss theorem, Birkhoff theorem are telling me, that when I have spherical symmetry, okay, then what's happening outside is none of my business. Okay, it doesn't affect actually what's happening inside. So I can actually go and solve for the equation of motion of this sphere, which is actually, we already solved it. These are the closed frequency solution, right? And then at the same time, for any kind of cosmology, I use whatever the cosmology is telling me. Okay? So it's a fantastic model from this point of view because we can learn a lot about it. Now it's clear, the perturbations are not spherical, and we have to take, we take into account, and things are much more complicated. But it gives us some kind of guidelines. We know if you know what's the original or the kind of amplitude we are talking about, we know more or less within the factor of, unity or very few, what's the maximum expansion phase, what's the collapse time, what's the typical density that we expect to find in collapse of this and so on. And so it's a very good tool to have in your toolbox. Right? So bear with me, stay with me now. We're going into kind of a long technical journey of how to do the details of the complex model. But as good physicists, what we want to do before is to say, before I'm trying very, very hard, let me linearize the equation of motion. Let me see what happens in the linear regime. Now, linear regime, I mean when the overall density is small compared to the background density. Okay? That's what I mean by linear regime. So what I want to do right now is actually to derive a linear relation, a linear equation for the evolution of the data rho that we have here. All right? And then, tomorrow we'll do it in full glory in the most general case. without assuming any symmetry. But right now, I think it's a nice exercise, and I want to do it with you here. Okay. So essentially, what I have like two things. First of all, I know the equations of motion. So I know that R double dot equals to minus 4 pi g. All right. I'm looking first at the, let me look first at the output term. So I have two spheres. Okay, there, okay. Now the R that I'm using here is not this, I'm not calling it like, you know, lowercase r, I'm just calling it R, you know, capital R. Okay, so capital R bar corresponds, so if I'm changing notation, so this is just R at some time I, and this one is R bar at some time I. Okay, now I'm writing the equations of motion for R, both of these radii and the function of time. Okay, so what I have here, I mean, I know it, I already did it to write it, wrote it yesterday, so it's time rho bar, sorry, times R. Okay, well, rho bar, I mean, all bar quantities here refer to the untotaled universe. And I have something very, very similar to the perturbed universe. Everything is the same, even the pi and the 4 and everything. So it's minus 4 pi over 3 times g times rho bar. But now it's like 1 plus delta times r. And with delta I think is the most useful Greek letter or character that we are using in structure formation. Okay, so delta, maybe delta and rho, I don't know. Somebody should, Stefan, you did in the book meeting, this kind of counting the period, the number of periods of characters or words, right, in text. You can do it in the end of the meeting, of the school to find it out. All right, so delta is just divided, rho minus rho bar divided by rho bar. So what's the delta? Is the over density, okay, rho minus rho bar, normalized by the mean density, okay, and for delta is dimensionless. All right, and we start actually with delta is very, very small. The amplitude of delta is very small. All right, so we have this. That's the equation of motion that we have. And, well, okay, so now we assume that, I mean, right now, I'm assuming that I have no, I don't have any other component. The only component that I have is like I mean, it's called universe. So it's the rho bar here, and you forget about the rho lambda. And so what we have here is the following. I'm assuming mass conservation during the expansion of both the universe, the unperturbed universe, and the conservation, the top hat sphere that I have. So what I have here is rho times 1 plus delta times r cubed. Now, except for the one that appears here and the equality sign, everything here depends on time. So rho changes with time, r bar changes with time, and delta changes with time, and r changes with time. Okay? So what I have here is at the end, you know, I can think of the rho bar. So what I have is r over r bar equals to 1 plus delta. So you remember, everything here that I'm writing actually is a function of time, okay? And now comes the critical stage where I'm linearizing this relation, okay? So what I have to write is r over r bar, okay, equals to the first order. So it's 1 minus delta divided by 3. So this relation, this is a linearizing the term that I have here. And that's what I'm getting. Now, what we have to do is the following, okay? So if you wish, you can write R of t equals to R bar of t, I'm writing it explicitly, okay, times 1 minus delta of t divided by 3 plus higher order terms that I'm forgetting, okay? So what I want to do is actually to write down the equation of motion, like these are the full equation, the full nonlinear equation, but I want to linearize the equation of motion. So I'm leaving it to you, for you as an exercise, and we can do it sort of together in the session afterwards. And you can just try it. It's kind of fun to do it, and be around to help if you get stuck. It's not a big thing. And actually, so what I'm getting is that linearizing this relation, I'm finding that actually, so that's, I mean, the transition from here to what I'm writing here is left for you with, as a kind of a small exercise. So what I have here is R double dot over R equals to, let me write it. Okay, I'll write it like this. No, I'll just write it in a bit more symmetric way. So minus R bar double dot over R bar. I'm writing it equal, but it's equal within the linearized, after linearization, okay? So I have here that's equal to minus, it equals to minus a third times delta double dot, minus 2/3 times R bar dot divided by R bar. Now this, what is the term that I wrote here? What's R dot over R for the total building? What that? It has a name. He was a lawyer, he found something about the extent of the universe. Hubble constant, okay? Times delta dot. All right? Now, I know that actually, when I'm taking this equation, okay, I can divide it by R, and I have here R bar double dot divided, R bar equals to, the thing times rho bar. I have the same thing here for the perturbed cases. So what I have actually, if I'm taking these two equations that I wrote here, okay, divided by R bar or dividing by R, and subtracting one from the other, then I find that actually R double dot over R minus R bar double dot over R bar equals, now this is exact, minus 4 pi G over 3 times rho bar times delta, right? You see, I mean, going from here, are you following me? All right? Okay, and we have it here. So we have actually the same expression on the left-hand side for these two equations. We can combine them, and what we get at the end, you get one of the most famous equations, or the most important equation that we have in structural formation, and that we write it here, delta double dot, second derivative of delta, plus 2 R dot bar. Okay, like that, and that's nothing more than the Hubble constant as a function of time, times delta dot equal to 4 pi G rho bar delta. And so we got a linear equation for the derivation, for the time evolution in the linear regime. So this actually equation holds only as long as the amplitude of delta is much smaller than 1. All right? And then we can sort of solve it. And the nice thing about this equation, I derived it here only for the case of spherical perturbation. I'm going to show you tomorrow that actually this is the general equation that we found for any general any general perturbation. It doesn't matter if we have another component like the cosmological constant. I mean, as long as what we have here, the rho that is written here, is the component which we are perturbing its density. Okay, then this is a very general solution. I mean, so tell me what's your cosmology, namely how the mean density of the universe changes as a function of time. Tell me, and then if I know what's the cosmology and I know what's the Hubble constant, I plug it in the equations, and then I can solve the equation. One or another, I can solve the equation. Okay? So it's kind of a nice thing that comes out from the complex model, but that's only the foreplay. Okay, it's only doing the linear thing, and next we're going to do the full nonlinear evolution. All right. So what I'm going to ask you to do in the session afterwards is, first of all, just to finish the derivation. Essentially, there's only one step that is missing. A few minutes, maybe more than a few minutes, maybe a bit more, but it's very simple. Then you go from here to here, you get this equation, and now assume an Einstein de Sitter universe, namely flat omega equals 1, only cold matter. Then we know how R behaves as a function of time. We know how the mean density behaves as a function of time. And then just solve how delta evolve as a function of time. Okay, so that's going to be part of what we're going to do, and I'm going to ask you to do in the next session. Questions, comments?
That question there, what do you do to invest quality? I didn't understand.
This one?
Yes.
This expression actually expresses mass. I'm sorry. Let me. Yeah, I'm assuming that I take the initial radius. Okay, I take the initial. I mean, the radius of the. It's a good question. What's your name?
Guido.
Oh?
Guido.
Leo?
Guido.
Guido? All right. Forgive me for my. I'm slow with getting foreign name. Okay. So what I'm saying, you know, just a trick. I mean, I can take any kind of a sphere that I want for the unperturbed solution. So I'm just taking such a sphere that some initial time, actually, that the total mass within our bar, okay, equals to the total mass within the top head, okay, and then the rest follows. All right? I didn't say that, should I say? Okay, but it's really. All right. So now what I want to do is actually to do the top head in. I'm sorry. Other questions? Other comments? Whatever. Okay. All right. So.
When is valid to take into account the linear model?
You know it very well. When you have the delta, the amplitude of delta is much smaller than 1, then you can take it.
But in what stage of the universe we can take into account this?
We'll get to it. All right. Suppose that we talk about suppose that we have a very simple model that corresponds with the top head. We think that we want to have like a top head perturbation, like one single circle perturbation that is going to collapse and to turn into a cluster of galaxies. So and let's say it finishes the collapse, like this kind of final state of it happens today. Okay. Then we say we're going to calculate actually what's the density of the object today, and if I know, if I'm imposing the condition that it is collapsing by today, then I can tell you, or you'll be able, after the session of this, afterward, and the homework session that we're going to have, you'll be able to calculate what's the initial over density that I need to have at what redshift in order that this kind of perturbation will collapse today. Now, whatever is the collapse, whatever is the objects that you have today, okay, as long as you look at it as a spherical perturbation, it's clear that at some early stage, you're getting very, very close to the unperturbed solution. When you're getting very, very close to the unperturbed solution, it means that the delta is much smaller than 1. Okay? So as long as you have things that are like smaller than 10% or something like that, then you can go ahead with it. But physics is always cheap. So maybe you say, okay, I'll push it a bit more and so on and see. And maybe I need to do some correction, and maybe I'll use, second order or something, and talk about a different kind of approximation of how to do it. But that's the idea. All right. So to answer I'm just reversing your question, and I'm telling you, for each perturbation that collapses at any given time or redshift or whatever, you can always find an early phase where the delta, the over density with respect to the unperturbed universe, is small, and then what the equation that we derive here, or the final equation that I derived here, is valid. And you can use whatever relation that you have. We call it the linear theory. On the linear theory. Yeah. Your name?
Juan.
Juan. Okay.
So once we're approaching like the collapsing point, the right side of the curve, then this equation, this condition will be violated, right? The over density will grow that much. So what will be the behavior of the curve when you go beyond the linear approximation?
Time before 10, and I have to finish. I'll be able to answer.
I'm wondering, this is kind of cartoon to explain why the universe is expanding, galaxies are not. But they are also not collapsing, right?
There is some kind of virial equilibrium. Okay, I'm not going to discuss the virial equilibrium with great detail, although a lot can be said about it, and I spent a lot of part of my career actually trying to calculate this kind of thing, but it's kind of very messy, complicated. I'll just say about it a few words. We don't have much time to work on it. All right. Can I do nonlinear? Are you ready for the nonlinear? Let's go nonlinear. Okay. Let me erase it, and we start to do the nonlinear. Let me add, actually, while I'm sort of talking with my back to you, that most of what we know in structure structure formation that pertains to the dark matter, where we have no dissipation and then we have just gravitational dynamics. Actually, most of the analytical understanding that we have actually is derived from the Topaz model. So, in spite of the fact that it's a spherical model with lots of, it's a big assumption that we are making, actually this is almost the only game in town, if you wish, the only tool that we have to be able to make some kind of analytical prediction. All right? We want to go beyond that, then we have to listen to Stefan, then we have to do simulations. Okay, where everything is sort of done with great detail, and we try to imitate what's happening in full detail numerically. Okay, so you have like two ways to proceed. One is like what I'm doing now analytically, and then like next week you do it numerically. All right. So topic. I'm looking at the mass of a perturbation, so it's the same kind of story. I want to, I owe you a big apology, and I'll tell you what it is. I'll say it immediately right now, all right? So we are going to consider a universe with only two components, lambda term and cold matter, okay? And when I derived actually, I did a project to calculate all of the things that I'm going to ask you to calculate. I did it as a kind of a summer project with an undergraduate student in Jordan. And then when we wrote it down, we used some of different notation from what I'm using here. So let me ask you to excuse my change of notation. So what I'm going to say is that the omega matter that we had before, actually we are going to replace it by omega naught. So when I'm writing from now on, omega naught, it's not the total omega, it's the omega that corresponds to the dark matter, to the cold matter, I'm sorry. And instead of using this omega lambda, I'll be using that small case lambda that I have here, okay? So, and I'm going to define it very short, okay? And I'm going to use the notation that I'm going to use, so just keep it in mind, okay? It will come up very shortly. I'm going to write the mass of the perturbation, okay? So now I'm just writing I'm looking at the top hat, the perturbed part of the universe, and assuming it's spherical symmetry, and I write it, the total mass is 4 pi over 3 times rho bar times 1 plus, I'm writing the initial over density by this kind of capital delta times r cubed. Now, this is true and valid at any given time, because we assume, mass conservation, and it's a sphere, and so everything that is enclosed within the sphere is going like that. And in particular, it's valid in some initial time. Okay, so I'm assuming that I can look at the perturbation when the perturbation was very small, namely the value of the delta here, which is the same as the delta that I wrote just before. Okay, is very small. It can be either positive or negative, depending if I want to look at the. Yeah, I mean, in the same story, the same top hat actually can be used to describe the voids, big empty regions in the universe that are expanding faster than our unperturbed universe. But we are going to concentrate here only on positive perturbations. Okay, so this delta is some initial time. So I have to assume an initial time. I'm assuming that the initial time is much smaller than the present time, and therefore the delta I, and I have here Ri, are all, early enough that the delta I is much smaller than 1. Okay? Now, I can say that the total energy of the perturbation, from my point of view, what we are using here, energy is energy per unit mass. Okay? Not always I'll say it, but keep it in mind if I talk about energy per unit mass. Then, actually, what I have here is R dot squared minus Gm over R. Okay, and actually, what we have is, and I have it here like that because I'm doing it per unit mass. Okay, if it was not per unit mass, I have to multiply it by the mass of the perturbation. Okay, so now, because of the symmetry and so on, I'm assuming that I have energy conservation as well. So the energy is in particular equal to the initial energy that I have at my initial time, initial epoch. And now I'm making the assumption that the perturbation, this top hat perturbation actually expands at the initial time at the same rate, at the same speed like the rest of the universe. Okay? So I have here, it's half hi squared times ri squared minus now 4 pi over 3 times g rho I bar times 1 plus delta I times ri squared. Okay? So that's what I'm having here. Okay, so that's the initial. So what I have here two conserved quantities that I'm going to use all along the way. That I know that the mass is conserved, I know that the energy is conserved. Okay, and so that's what I'm going to use from now on. Just rewriting it in terms of omega and critical densities and everything. So what I have here, I can write it. It equals to half hi squared ri squared. Now, what I have here, I have, like, I'm pulling the factor of half outside of the parentheses, so I have here 1 minus, and we'll talk about what it is. So from the half that I have here 8 pi, and I have here h. I mean, the dependence on the initial values, in both cases, I have ri squared, okay? So I can pull it out here. And I have here an hi squared that I'm pulling out of the parentheses, so I have to divide it by hi squared. So again, I'm getting here the critical density. And so what I'm having here at the end is 1 minus omega I times 1 plus delta I, and that's, so the initial energy of it's the total energy of the perturbation that is conserved all along the way, can be expressed in terms of the initial phase. Now I have here hi, omega I, that actually refer to the unperturbed universe, okay? And so I have here now a relation, R is going to change as a function of time. Delta I is whatever I choose, for the initial perturbation, you want to change. So I can express the total energy by mixing the properties of the unperturbed universe and the perturbation that I'm choosing. Now I want to say one thing that is critical here. I mean, the choice that I made here of assuming that there is no initial velocity perturbation is one possible choice. One can very easily rewrite things where one is perturbing both the density and the velocity. Okay, we'll see that it leads to two different kind of going mode, decaying mode, and so on and so forth. But I want to just draw your attention to the sense that I made here a very specific choice. It's not the only possible choice to make, but that's a choice that I made here about the initial perturbation that I have. I'm perturbing just the density and not the velocity. Okay. So, and now we consider here what else? Yeah, I can write it half hi squared I squared omega I 1 over omega I minus 1 plus delta I, and I can use it later on. And now we are talking, I can look at any kind of perturbation that I want. I can look at it and follow it and calculate things with any value of delta I that I have. But we are interested in bound perturbation. Namely, we are interested in using this kind of model, the top hat model, to account for the formation of galaxies, clusters of galaxies, and so on. So, namely, we need perturbations that are bound so that the radius of the perturbation will reach some maximum values and then we collapse. Okay? So, the condition that we are going to use through the derivation that I'm presenting here is such that the perturbation is bound. If we are dealing with the background being an Einstein de Sitter universe, then for any positive perturbation, the perturbation is bound. Okay? But if it's an open universe, or it's a universe with a lambda term, and so on and so forth, then we need to make sure that we have a bound perturbation, namely that the total energy of the perturbation is negative. Okay, otherwise we get this solution. Okay. So now we recall that the actual equation of motion that we have, we already wrote it a few times here. So that's the equation of motion. Okay. And it's called, and the equation of motion actually that we are looking at a particular equation for a bound solution. Okay, and we already had it. We already had it. We divided it. That's the solution of the Friedman equation for omega larger than 1. Okay, so when I'm writing the result, what I'm getting is the space here. So I'm getting actually, like from these two things, I'm getting that I can write R to be some constant A times 1 minus cosine theta. And I have here T, which is like a B times theta minus sine theta. By now, you know this solution. You should dream about it at night. Okay. Besides the other dreams that you might have. Okay? And when you plug in this solution and so on and so forth, you find that actually the relation between the A and the B is A cubed equals to Gn. And this was actually you used it yesterday for the timing argument mass expectation that we had. Okay? Again, the cartoon thing that we have here for the perturbation. So when we look at it, we say that's the radius of the perturbation. Okay? Starting at some very early epoch, so it's like very close to 0 time, so it goes like this, right? And the epochs that we are interested in are the one at which the density reaches maximum expansion, right? And so we want to actually define it and to relate it to the initial conditions. Okay. I mean, there are different ways of getting this type of maximum expansion, and so what I'm doing here, what I want to find out is R max. Okay. Now I know that the time of maximum expansion, then what's the speed, what's the velocity of the edge of the perturbation of R? It's 0, right? Because it's just telling you R. Okay. So when I'm writing, so what I have here, that actually the energy equals to Gn over R max. I know what's the energy, I have it here. I know what's the mass, I have it here. Simply that I know what's the G. So then what we have is we write it like how do we write it? So it's minus Gn over Ri times Ri over R max. Okay. Now Gn over Ri, I know it actually because I know what's the mass expressed in terms of the quantities here and in terms of Ri. So what I'm getting here is that this quantity equals to, so the quantity that I have here on the right hand side is equal to minus half Hi squared times Ri squared omega I 1 plus delta I. I'm sorry, I have here Gm over Ri, Okay. And so what is it? So GM over RI, so here for a second. Oh, I marked it for myself that actually I have to cross out this thing here, and I'm just leaving it here for me and for you to prove it later on, so I don't see it here on the blackboard. But it's actually, it comes from substituting actually the GM of our RI that I have here, and I'm relating it to the initial delta. Um, 1 plus delta I divided by delta I minus omega I minus 1. It's 1 over omega I, I'm sorry, minus 1. And that. Okay, so essentially, or if you wish, I can write it is that R max divided by Ri equals to, now I know that I'm starting at some very initial time where delta I is much smaller than 1. Okay, so so actually what I have here is the following. So I have here 1 plus delta I. So delta I is much smaller than 1. Okay, and I have here, so it's 1 over delta I minus, so like to first order, so it's delta I minus omega I to the, it's 1 over omega I minus 1, like that. Okay? Now, for the case where we're talking about, flat universe with omega being equal to 1, and omega I also is 1, then we have here 1 minus 1. So this actually can go away. And what we are left with is actually the ratio of the maximum expansion values divided by the initial one is just the inverse of delta I. Okay, the larger is delta I. Okay, the larger is delta I that we have, what happened to R max? It's smaller or it gets smaller or larger? Smaller. Namely, the more bound you make the perturbation, the more metal you put inside, actually it will reach its maximum expansion earlier and collapse earlier. Okay? And at the same time, when you make delta I to be smaller and smaller and smaller, then R max becomes larger and larger and larger, and then actually the perturbation stay closer to the unperturbed universe for longer and longer time. That's like it's a partial answer to what you asked before. Okay, so we have now this R max in terms of thing. I mean, I just missed here like one step. I mean, just a combination of this omega, M and energy expressed in time units of the initial time, and we're here. Okay, now we know that the maximum expansion phase happens, or time, or the phase that we have of R max right? It happens when theta equals to pi. Okay? If you remember that we have here the parametric solution, so it happens when theta equals to pi. So, and now we know that R max equals to 2A, okay? And so we have that the A, the solution here, equals to Ri divided by 2 times 1 plus delta I. I'm just giving you alternative without throwing them away. Divided by delta I minus 1 over omega I minus 1 like this. Okay, we know what's we know that vector relation that A cubed equals to the mass G times the mass times B cubed times B squared. Okay, we know what's the A, it's written here. We know what's the M. The M is written here, okay? Or we can, yeah, get it there, okay? So when we combine it together, what we have at the end, we have just a bit of algebra, do it yourself, but you are redividing this whole thing. Then we have here B is like 1 plus delta I divided by 2HI omega I, so it's the power of 1/2, so it's square root of omega I times delta I minus 1 over omega I minus 1. This whole thing is the power of 3/2. Okay? What we have at there. Okay? Now, just to get some kind of a feeling and so on, if we assume that we have an Einstein de Sitter universe, so I just want to see, you know, it's not kind of complicated. I mean, look at the expression, okay, the algebra gives you something like that, but I mean, you don't get lots of sense of what we have here. Now, for the case of an Einstein de Sitter universe, things get simplified because omega I is 1. Okay, so the assumption of Einstein de Sitter universe actually the assumption that the omega is 1. Okay, and then what the relation that we're getting is that A equals to Ri over 2 times 1 plus delta I divided by delta I. And the B that we get is 1 over 2HI times 1 plus delta I divided by delta I with the power of 3/2. Okay? If we say that we are sort of linearizing things, that we can throw away the delta I that we have here, we can throw away the delta I that we have here, and we have things that are we can relate like then time here, and radius is a very simple way. Okay, so we have the solution. We know how R and T are evolving as a function of time. I mean, that's the basic solution that we have. Okay, but now we express the A and the B that we have here in terms, so that's a general solution. Okay, you find it in any textbook, and that's what you get from the Friedman solution. What I did actually in the last sort of 10 minutes and so on was actually to go and to take the A and the B and express them in terms of the parameters that define the perturbation at some initial time. So I know what the initial values, I know what's the initial density, I know what's the omega at the time, that's the cosmology, I know what's the Hubble constant at the time, I know everything here, and I have a solution. Okay, I have a solution for R and T, you know, as a function of this parametric thing. If I'm clever enough or I'm willing to work a bit harder, then I can write that it's actually either t as a function of r or r as a function of t. Nice. But we want to go and do things beyond actually this, and we want to see how the density is evolving. Now, we want to see how the density is evolving, not only in terms of the density itself, we want to see how the overdensity is evolving. Namely, not only to look at the density of the perturbation of the okay, but also to see how the density is evolving in contrast or compared with the unperturbed universe. Namely, we have to follow what the universe is doing, we have to follow what the perturbation is doing, and then to start a comparison. Okay, that's the nature of the game that we are doing here. So let's convert from radius as a function of time into density as a function of time. Now, it's not so difficult because we know how the density is changing. The density is changing like 1 over r cubed. Okay, and so if I want to change it as 1 over r cubed, I know how r is changing as a function of this theta. So eventually, here, staying with this within this solution, everything is given here in terms of this parameter theta that define the orbit that we are dealing with. Okay. So what we have here, that the density is changing the function of time, okay, which is just the mass divided by 4 pi over 3 times r cubed. Okay. Now the r cubed actually is given here. Okay. So what we have here is equal to 3m divided by 4 pi divided by 8 cubed. Okay. 1 minus cosine theta cubed. All right. And rho of t is the evolution of the okay. See that it takes me much longer than what I expected. Now I want actually, let me stop here. Actually, this is the case, although we're not living in a university in the answer to theta, but it's a kind of a limiting case that it gives us a lot of intuition. Okay, and you find lots of in the literature, a lot of the derivations are done with respect, first of all, to the answer to theta. So let's follow this kind of tradition, and from now on, I'm just assuming that we are living in an answer to theta universe. So I'll get all sorts of relation in order to motivate us, so to get some feeling, where things are also more analytical when we are dealing with the answer to theta case. Then the next thing that we'll do is actually to extend it to the more general case. Okay, so what we have here, so let's see how the answer to theta case is evolving. We know that for the answer to theta case, we always have h times t equal to 2/3. Okay, we know that because of that, we know that h squared, t squared equals to 4 over 9. Okay, we know that omega is 8 pi g divided by 3 divided by h squared. And we know because it's an answer to the theta case that omega, sorry, times rho, is always 1. Okay? Now, if I know, so I have this relation. Now I know that actually h is a function of t. Okay, t equals to 2/3 times h to the minus 1. So I'm using actually these things and I'm combining it together. And what I'm getting, so here is like for the unperturbed thing. So it's the rho of the unperturbed universe. And what I'm getting here, is that rho goes like 1/6 pi g divided by t squared. So that's the density evolution of the Einstein of the theta universe. Okay, and so what we have here, if I want to now, I'm going to keep it here, okay, because it's so important, and I think that we'll get back to it. So I'm going to go around this. You see, maybe that's why we need more space. Okay, I just keep it here, so we'll give it for reference. Okay, so if I want now to follow the evolution, so now I want to get the delta t, not only at time or the initial time, this delta I that we had going all along the derivation that we had. So delta of t is nothing more than rho of t. So it's the rho of the perturbation that we have here, divided by the mean density of the universe. Okay. -1. Now, I have it all here. It's tedious, I have to collect terms together, but it's all here. So, bear with me and let me do it. If you're getting bored with the derivation, let me tell you that in most textbooks, you don't get the full derivation. Nobody's doing it for you, or in very few books you get it. And at the same time, it's very, very important to have it. It's very, very important to be able to do the calculation and to get the critical characteristic density and so on and so forth. Most physicists or most cosmology are just using approximate, some kind of fitting formula that they take from some papers. Very few people calculating this thing by themselves. So I hope that you'll be one of the few that can actually calculate this thing by yourself. So that's why I'm sort of trying hard with it. Okay, so what we have here at the end is the delta of t is 6 pi times g d squared. Okay. I'm sorry, I missed to tell you. So just copying from what I have and substituting what I have here again. So, 3m divided by 4 pi a cubed times 6 pi g b squared. So what I'm having here actually, so for the density of the unperturbed universe, I have things that are going with time, okay? So the things that are going with time, I have here a combination of b times this theta minus sine theta. For the perturbation itself, I have here the density of the perturbation that is given here, and then I have here the a cubed and the 1 minus cosine theta. So when I'm calculating this, all of it together, I have here 6 pi g b squared times theta minus theta sine theta squared divided by 1 minus cosine theta cubed, all of it minus 1. Now I'm taking the derivation, the expression that I had for the a and the b. I'm taking this one and I'm plugging it here. And then what I'm getting is something that becomes simple. So delta of t, I'm sorry, I don't have delta of t, I have delta of theta, because I haven't solved for t yet, okay? But I can do it if I want later on. So delta, I think, the function of theta is 9/2 times theta minus sine theta squared divided by 1 minus cosine theta cubed minus 1. Okay? Yeah, I see that I just finished the case of the answer to theta diagonal. So if you are happy just to get theta as a function of theta, you are fine. For example, if I want to get the over density of my perturbation with respect to the universe at the time of maximal expansion, what I have to put, I know that maximal expansion corresponds to theta equal to I. So I'm putting here, I'm substituting pi for theta, and I can get the value. Okay? I just want to do a bit of more massaging the equation that we have here. And I want to define here two new variables. Maybe I want to relate the initial time and the initial over density to some quantities that are related to the present epochs. Okay? So I'm defining by the parameter x, or the variable x, this Ri times r at the present time, so it's the time of t naught, time divided by r. Now r corresponds to the unperturbed universe. Okay, so this quantity actually is nothing more than Ri times what do we have here? 1 plus Ci, right? Okay, and I'm defining delta naught. So it corresponds to the original over density that I have in the following way. I have here, for reasons that will become clear later on, 3/5 times delta I, and then I have here R naught divided by R Ti. Ti, okay? And so delta naught actually is nothing more than 3/5 times delta I times 1 plus Di. So somehow I'm relating actually the original quantity that I had at time I to values that had some meaning today. Okay, I'm normalizing it by the scale factor of today, and I'm writing also, I'm doing some kind of similar trick to go from delta I to some density that has some meaning today. Okay, but from our point of view, it's just a definition that I'm going to use and to substitute. All right, so what I'm getting at the end, I'm getting that I'm taking into account that actually now that the delta I are small, and so I'm getting that A equals roughly 3/10 times x over delta naught, and B equals to 3/5 to the power of 3/2 times 3/4 times t naught divided by delta naught to the power of 3/2. Okay, and I think that I'm done. Okay, so I want to collect everything that I wrote here and to see what I'm learning from it and what we can divide from it. So the final result that I'm getting from the top hat model with in an isodecita universe is the following. I find that R of t equals to 3x divided by 10 times delta naught, 1 minus cosine theta. T equals to 3 fifths to the power of 1.5 times 3 times t naught divided by 4 delta naught to the power of 3 halves. This is time theta minus sine theta. We know that t over ti goes to the power of 2/3, goes like 1 plus v divided by 1 plus vi. That's for the unperturbed solution. Then we know that actually I can write, instead of writing using the time as a coordinate, I'm using the redshift as a coordinate, okay? So I can write 1 plus v equals to 5/3 times 4 divided by 3 to the 2/3 times delta naught divided by theta minus sine theta to the power of 2/3. What else? I have another result. Oh, okay, never mind. We have done it. It's the end of the class. And then we have the delta equals, delta equals 2/9 times theta minus sine theta squared divided by 1 minus cosine theta cubed minus 1. I'm reminding you that we use the definition delta naught equals to 3 halves delta I times 1 plus vi, and x is ri times 1 plus vi. So delta naught and x are actually a different way of expressing ri and delta I. Okay, at the time I. Okay, so the time I is given by the redshift here. And so if I know what's x at the time I, or the redshift I know what's ri. If I know what's delta naught, and I know what initial redshift that I have, then I know what's the delta I. Okay, now I'm done. I know everything that I wanted, that I need to know about the behavior of top head perturbation in an Einstein de Sitter background. And let's see what we can get from it. Okay? Let's say that we just take theta to be some, any number. Okay? We know that on this trajectory that we had actually this trajectory. Okay, actually, it could have been a trajectory in theta, where this is theta of 0, this is theta of 2 pi, and that's the theta pi corresponding to the maximum expansion. Okay, so if you want to follow your protections to your perturbation, you can do it as a function of theta. All right, and then you say, okay. So first of all, we have to specify the perturbation that we have. Namely, tell me what's the vi that you want to have. Tell me what's the initial overdensity at that time. I mean, time and redshift are similar here. And tell me what's the initial radius that you have. So vi, x, and delta naught is like saying vi, delta I, and ri. They are just the same. Okay, another way of writing it down. Okay, so then if I want to know how the overdensity of my of the perturbation is evolving as a function of time, I have here. I just have to plug in the theta and I can find it out. Okay, if I want to see how the density, how the radius is changing, Now I have to put here a number. I mean, this is a quantity. I mean, this quantity here is dimensionless, and it depends only on theta. If I want to find the radius, okay, then the radius is actually, I have to express it in terms of the theta and the x and the delta naught. Okay, time is the same story, and the rest of it follows here. I can do it in another way. Okay, I can say, okay, what's the I'm saying instead of specifying the time or the theta, I'm specifying the values. Okay, I take the values, I can solve this equation for theta, right? By the inverse cosine. Okay, I find for given values and given the initial perturbation, I'm solving for theta. Then I can find the time. Okay, I can find the time, I can find the wedges and so on and so forth. And now I can also, for that given values, I know what's the delta. What's the over density of my perturbation with respect to the rest of the universe, and so on. Okay. Now, is there any way, or I'm going to speak 5 minutes from there? 5 minutes. Okay. You see how kind is Simon to me? You know, now I want to tell you something kind of general. Okay. That I mean, we are all very, very fine up to this point. Okay. Namely, up to the epoch of maximum extension. If we really had a this kind of a perturbation, a topic perturbation, and so on, then it can be kind of a reasonable approximation when we are actually following it from the very beginning up to the point of the maximum extension. But then we say after that the spheres start to collapse. Okay, when it first starts to collapse, actually everything is fine. Okay, but when it reaches the final crunch, actually it's clear that the assumption of homogeneous sphere that we have starts to break down. Okay, if we had that the sphere is really perfectly homogeneous within itself, right, and the density is really constant in terms of the spatial variation, then everything will have been fine, and we will reach the final state will be kind of a crunch, like a singularity. We start with a singularity and we end with a singularity. But if you look at the fact that actually it's this kind of a model that should correspond to like a galaxy or a cluster of galaxies that are collapsing, then this kind of a sphere is already made of objects that collapsed before. Okay, so it will never reach this kind of state that we have right here. What we are going to have actually, kind of the orbits are going to mix, and we are going to have some kind of I would not call it chaotic, but some kind of a random exchange of energy between the particles and between the lumps of matter that make this kind of perturbation. And it will never reach this kind of final state of infinite density with zero values. Okay, what will happen that actually this kind of perturbation, after a time, which if this will be a function of time, so going from T maps to twice T maps, we are going to get some kind of statistical equilibrium. Okay. And the system is going to settle in what we are calling virial equilibrium. Okay. Now, the virial equilibrium, we know that twice the kinetic energy, right, equal to minus the potential energy. Okay. We know what's the total energy at maximum expansion. Okay. And if they have no cosmological constant, we just have cold matter, normal matter, actually, then a very good approximation is to say that after about twice the maximum expansion time, we are reaching a time where the system is in virial equilibrium. In virial equilibrium, we can calculate and I leave it to you because I'm already taking more than 5 minutes, okay, that in general equilibrium, you can show that actually the final values in some kind of statistical equilibrium is about half the values at maximum expansion. Okay? So after that phase, I mean, everything is kind of fine and so on up to somewhere around here, around turnaround or maximum expansion. But then, nonlinear dynamics actually kicks in. I mean, the dynamics become very, very complicated. And the assumption that we make that the system actually gets its final density when the values changes by a factor of 2 from the maximum value. So if you want, you can actually take the kind of expression that we had here and to say, okay, I want to have a system that is collapsing by today. Okay, collapsing mainly reaching this real equilibrium and that today equal to twice Tmax. Okay? And I'm saying, okay, so now I have the time. I know that the time of maximum expansion is actually theta equal pi. I take twice this time. I can follow what happened to the perturbation. I'm just saying it's collapsing by a factor of 2. Okay, so I can relate the density at maximum expansion that I have, like from here, with the final density. I know what happened to the universe when it's expanding, this extra time from Tmax to twice Tmax. I know what's happened to its density because it's an isomorphic universe. And then I can calculate, actually, I can relate what's the final density that the collapsing object that collapsed by today. I mean, how it's related to the initial condition. Okay. I was too ambitious, and I thought that I'd be able to do like this 1.5 hours this morning to do the more general case, okay, and not only guys in the theta. But that's what I managed to do, and we took some kind of problem for you to do with guys in the theta case that we did here. So we're going to be 30 minutes. Thank you.
So now
let's talk about this.
no tanto porque es más, va a plantear el ejercicio.
I mean,